Welcome to La Nova Mobilidad. Today with a new episode of LNM Bytes. Hey, Miquel.
Hey, Martí. It's been a while since the last one we did in English. So happy to be here and also creating content for the guys that do not understand Catalan.
There's just a couple I heard.
Couple of them. There are a couple of them around. So what are we going to talk about today, Martí?
Yeah, we're going to talk about electrification, but as we talked a couple of weeks ago, electrification in space. And we have Johannes Kurtz. Hey, Hannes, how are you?
Good evening. Hello. Thanks for having me. Unfortunately, I can only record in English or German and not very fluent in Catalan.
Well, nobody's perfect. It doesn't matter.
Okay.
No, Hannes and me, we used to work together at BMW a couple of years ago. But well, you got several career steps we will go now through, and you're now going into space with battery development and production for aerospace, no?
Correct.
And that's going to be our topic today. But just go back to your start, Johannes. What did you study and where?
I studied electrical engineering in Munich. I was always focusing on battery technology and heavily focusing on automotive industry there. That's where we met in the end at BMW, developing the architecture of safe batteries for automotive applications. But after a few years in a huge company, I found out that I'm more interested in founding my own companies and working as an entrepreneur. That's why I joined after 2 years at BMW a tech startup in Munich called Lilium.
Mm-hmm.
That's a company focusing on electric vertical takeoff and landing vehicles,
Mm-hmm.
trying to revolutionize the means of air transportation. And there I was responsible for the battery management system architecture. So, how does the battery measure certain states? How does it compute these measurements? And how do we take actions to enable safe flight and landing? And there I met excellent people. Like it was a great atmosphere, a great environment. And from that environment, we assembled a team of engineers founding the company Excellion,
Mm-hmm.
where we are developing, building, and testing battery systems for aerospace applications.
So that's you made like 3 steps, no? Starting from the ground, from the road, then you went into the air with eVTOLs, and now you're just going into space. No, I think it's a good path, and I think we're going to go through, let's say, these topics and understand what is the electrification of aerospace. No, what are we talking about? Miquel, if you want to introduce the topics, maybe.
Yeah, so maybe to start, like, what are the different applications of batteries in our space, and what are the difference between them? Like, what are the different parameters that characterize the different applications on batteries? So,
Perfect.
quite open.
It's a wide open, which I want to narrow down already a little bit. So, aerospace composes of the two parts, aero and space. So, Excellion really focuses itself only on the space side of things. So, everything launching satellites into the orbit, starting with something like 400 kilometers of height. This is a field of technologies where there's a huge new development ongoing, the so called era of new space. And that's a totally different field than aviation, which I was
Mm-hmm.
working before. Aviation is really characterized by really strong means of certification because many people are at risk in these applications. Therefore, as a startup, we argued to focus on the space industry first because there we build systems for unmanned
Mm-hmm.
launcher systems and obviously unmanned satellites, and therefore it's easier for us to enter.
Mm-hmm.
You asked about the different applications for batteries in space in this segment. And this can also be divided again into the launcher, which is the vehicle bringing people and payload in the skies, and also into the satellite.
Mm-hmm.
Starting with the satellites, this is really important to think of the extreme environmental conditions which we have in the battery and in the satellite in total in the orbital
Mhm.
condition. So if the satellite orbits Earth, it's sometimes in the sun
Mhm.
and sometimes it's eclipsed. So during the daytime of that satellite, all the electrical demands and power demands are actually provided by the solar array.
Mhm.
So like your actually your home you could think of. And during
Mhm.
the nighttime, all your electrical demands are powered by the battery system. And due to the extremely high speed of these satellites orbiting Earth, this charging and discharging happens crazily often. So every 90 minutes, for example, you're going to discharge the battery and then you're going to charge it again.
Mhm.
And Marty, in comparison to an automotive application,
Mhm.
these are thousands and thousands of charging and discharging cycles.
Mhm.
So it's really for the battery system a requirement on having extreme cycle lifetime
Mhm.
and being able to withstand, obviously, the vacuum, the radiation,
Mhm.
extreme temperatures, and so on.
Mm.
Because
You're just going through the script, so we will discuss the requirements maybe later on. But just for understanding the applications itself, I mean, of course, we have the image of a satellite with a big solar panels, and of course the um, let's say the energy for this, not for the movement, because for the movement you already got into orbit somehow, and afterwards it's just like going um, around the earth. And but anyhow, you need for the electronics, for sending communication and so on, you need some energy stuff, yeah.
Right.
And
So,
even we were talking to Henri Crustan a couple of months ago, and he was explaining us the electrification of propulsion in space, like the satellites with electro sprays and other similar topics, where you need maybe a small amount of energy, of electrical energy on board, and that's where your batteries are coming into application now, I think.
right. For satellites, you can split it into all the payload power demands like communication payloads, Earth observation cameras, infrared cameras. All these services the satellite actually performs in orbit are mostly powered electrically.
Hmm.
Secondly, you have to have specific functions like deorbiting, like bringing the satellite, like changing the altitude, changing the
Hmm.
course direction of that
Hmm.
satellite. For example, for collision avoidance,
Hmm.
or for deorbiting means to bring down the satellite at the end of its lifetime, so that this satellite is not anymore blocking its orbit, but frees it for future applications.
Hmm.
And these specific actions require a lot of electrical energy. And this energy can be harvested during flight by the solar array, has to be stored, and then these maneuvers can be executed.
Okay.
I would like to go back to the cycling and charging and discharging cycles. You mentioned 90 minutes. This is a low Earth orbit. So
Mm,
most of the stuff happening and the innovation is happening in the low Earth, in the
correct.
geostationary and middle and mid orbits. It's more like the status quo classical satellites application that is going on, or is there also some innovation in the electrification that's happening there?
In the MEO and in the GEO,
Yeah.
these orbits are stronger controlled, and the it's not so. So first of all, it's not so easy to get stuff up there. So it's just from an energetic point of view, it's a high investment to get a satellite up there. And for a geostationary orbit, everything gonna shoot up there will stay there as long as we can foresee the course of actions of such an orbit. That means that the regulation is quite strict. Who is allowed to send stuff up there? Because if there happens anything wrong and it comes to a rupture of such a satellite and a generation of space debris, you really have a long-term problem up there. So many startups, from one hand perspective, are reluctant to send stuff in the geo because of the high cost, but also many services which are currently massively growing, like Earth observation and telecommunication services, are obviously working better from a closer view and a closer in a close-up condition.
Yeah.
And therefore, many of these business cases we are currently supporting, which are demanding for high reliable and safe and cheaper battery systems, are happening in the LEO, and therefore we're focusing on this product as well.
So there is application growth in the LEO, and then the entry barrier you mentioned earlier for avionics is high, and then it gets high again as you get far away. The entry barrier because of safety regulation, because of economic.
Leo is the lower
The lower
orbit,
orbit,
no?
something like a
With
400 kilometer. That's where the ISS also circles
okay.
Earth. This is also picked because of lower radiation, because of the magnetic field of Earth protects
Okay.
not only the electronics but also the human incumbents of the ISS from a part of the particles and radiation exposure from the sun. That's why for easy applications you pick the orbit which is closer to Earth.
And also protecting the battery, maybe a little bit.
Yeah, also protecting the battery. That's true.
But anyhow, maybe you said the energy amount, the power need for these satellites, it's not that huge and might have a high cycling during day and night in these 90 minutes you explained at the beginning. But the most powerful need is going away from Earth, no, starting with the launchers. And usually there we don't use electric propulsion itself. We use, yeah, hydrogen,
Right.
methane is using SpaceX and so on. But also these rockets are using batteries, no? For
They
what?
are.
For what, please?
Yeah, they are. Like a vehicle having to fulfill multiple functions in terms of controlling all the surfaces,
Mm-hmm.
powering all the computational platforms, but also providing power for the telemetry and communication services. And these extremely sophisticated and complex vehicles, like a launcher system, they are increasing more and more in their electrical demand. For example, we can measure the energy demand of the Ariane Group 5 or the Ariane 5 launcher system in comparison to the Ariane 6, which will finally fly end of this year.
Mm-hmm.
And there we see that the factor 10 increase of power demands
Mm-hmm.
already happened between these two programs. And
Of the
that's
electric power demand.
the electric power demand
Okay.
tenfold already in the last years. And this is mainly because of the services, as I mentioned, so avionics, telemetry, but also more complex control surfaces. And if you now think of a launcher system as it's developed by SpaceX, which is reusable, which has, like the Starship, massive control surfaces,
Mm-hmm.
really wings that are moving up and down, controlling the flight, not only towards orbit, but also back to Earth. There is strong evidence that Tesla is using, actually, sorry, that SpaceX is using Tesla batteries to
Okay.
provide all that electric power to the Starship. And these massive control surfaces are operated, moved by engines coming from Tesla, because this is really an extremely demanding electrical demand,
Mm-hmm.
electrical application.
Mm-hmm.
And therefore, there's a strong tendency to put more and more batteries into such a launching vehicle. And if you think that more further, there are already launcher systems where the propellant Martí mentioned, like hydrogen and oxygen, that these propellants are pumped electrically and they are not pumped anymore as they are currently done by a combustion cycle. So you can think more like a turbocharger, and this electric pumping capabilities offers a wide range of flexibility, offers great benefits in controlling the combustion process.
Yeah.
And lastly, if you really think launchers to the far-fetched future, And you think of launchers flying not only to a low Earth orbit, but further, flying to the moon, flying to Mars, you eventually have to rethink of how to handle fuels in the space. So refueling, pumping fuels from maybe one mission to another, refueling the Starship in orbit is actually a goal of SpaceX to enable the civilization of Mars. And that's all these processes and steps eventually will require electric energy. And as you see in the electrification of the automobile and so on, where electrification happens, you have to consider battery systems to compensate for these powers.
You mentioned Starship from SpaceX and Tesla batteries for the actuators for the surfaces, but they don't use it for the turbopumps, right? Like they have a different system on propulsion. But there are other startups, I think, like Rocket Lab, and from New Zealand. They think they use electric turbopumps, and there are also a couple of startups also in Germany that do that.
Correct.
So
The Rocket
um,
Lab Electra is the first or most famous example of an e-pump based launcher system.
yeah, are there also I think also examples in Germany? Oh, I think there is also a startup in Germany trying to do an hybrid propulsion system.
I cannot talk about that.
Okay, all right.
So we are now used we are used to the batteries for electric cars, which are, let's say, about 50 to 100 kilowatt hours, depending on the range we want to give the car, and also the size of the car. But how big are the batteries, and how powerful are the batteries which we are using into um, launchers and also into satellites, which might differ a little bit?
That differs a lot. Interestingly, it's really a wide range, coming from small satellites, having batteries just in the size of a little integration of four cells, like four cylindrical cells with a few hundred watt hours, going all the way up. We have we saw pictures of SpaceX having put a complete battery pack from a Tesla Model S with 100 kilowatt hours into the Starship because of these extreme high demand of a launcher system. And this derives an important requirement, which is modularity or scalability. So at Excellion, we want to build battery systems which can grow with the demand of the parent system. So a small satellite really gets just a few hundred watt hours because the electrical demands in such a small satellite are extremely low. But then we also can parallelize that battery system up to multiple kilowatt hours for larger battery systems. They are called small sats. Small sat being a class of satellites between 11 kilograms and 600 kilograms, and that's the largest share of all satellites in orbit. These are, for example, the Starlink satellites, being, let's say, as big as a large washing machine, having large solar arrays, and they tend to have a battery in the realm of 5 kilowatt hours. And if you then look into launcher systems, there are discussions, as I mentioned before, for e-pump applications, for refueling applications, of having really high voltage systems with multiple hundred kilowatt of power and multiple hundred kilowatt hours of energy content to provide energy for these demanding conditions. So it's really the complete bookend, starting from small, going to extremely high.
And what are the requirements compared to a car that moves on the ground? Like, do I need to be lighter? Like, you need more energy density so that you have more energy per volume, or more energy per mass?
So there's a strong optimization regarding energy per volume, interestingly, because these launcher systems, they have a plate where you mount all the satellites on, and that area where you mount that your payload on is really limited. So you only want to squeeze as many satellites and as many sensors and actually useful stuff on that launcher, and not so much weight in the weight perspective. So it's more like a volumetric energy density, which is super important. But actually more important than the performance characteristics as you know them from automotive, are rather the reliability and safety of these systems. Because as you have no mean of repairing anything you're going to shoot into a low Earth orbit, you have to be really certain that this system is functionable and that it's providing its function during the course of these 10,000s of charging and discharging cycles, being exposed to vacuum conditions, to also extremely high shock and vibration loads during takeoff of that very rocket. So you have way higher demands in the mechanical domain, again, against shocks and peak vibrations which are occurring during liftoff and during stage separation of that launcher system, then you would really optimize for the last gram of weight optimization. So you can really combine it to the mechanical domain, so vacuum, shock, vibration, then the thermal domain, which is quite challenging. So in a satellite, you obviously have to endure quite high temperature differences because of the exposure to the sunlight versus the eclipse phase in the nighttime. And then lastly, we talked a bit about radiation. In these atmospheric orbits, you are exposed to way more particles and radiation coming from the sun. And this radiation is gonna manipulate, if you want, your controller and maybe even destroying many electronic components. And therefore, we need radiation hardened electronic components, which are especially shielded or sometimes on a software level being protected by means of redundancy and error correction against this extremely harsh electronic environment.
Yeah,
So these are the most important requirements and therefore the optimization factors.
I wanted to go there to redundancies because, with your experience functional safety in the automotive, I guess there is quite a bit that you can also bring for aerospace, right?
Absolutely. So for space, it's really interesting to think of how redundant and how safe such a system has to be. So for a launcher, so if you're part of a launcher vehicle, it has to be extremely redundant and extremely fault tolerant because that mission you're gonna launch is so expensive. It's really just a price optimization. If there is a manned mission like with human beings, then it's a totally different discussion because then it has to be as safe as, well, hopefully an aviation program. Therefore, in an unmanned domain, it's really a cost optimization. How much do you want to invest to be sufficiently safe to not endanger your mission? For satellites, that's really changing now. So, due to the reduced cost of a launcher, one can accept that if I send 10 satellites into low Earth orbit, which are comparably cheap, I can accept that one of them is maybe failing because I did not add triplex redundancy, having a team of 100 engineers developing this to the end. So, for example, SpaceX is operating more than 5,000 satellites for Starlink. Many hundreds of them are not operating anymore. Hundreds of them are already in the phase of deorbiting. So this is really a change in the philosophy that space industry doesn't have to be absolutely robust against loss of mission. It has to be an economical, viable approach, and therefore one can accept that systems are less redundant as they have been maybe 20 years ago when it was extremely expensive to send one satellite into the skies.
Yeah, really interesting this evolution in the economics. But this may change again if at someday we say, hey, we have too much stuff in low Earth orbit. Maybe we need to be a little bit more sustainable, and we cannot allow to just put more and more stuff there.
The low Earth orbit is characterized by the fact that you have residual air particles in that orbit. So there is a natural tendency to
Degradation.
There's a regulation. So that's why I differentiate low Earth orbit as the future growth segment from the geostationary orbits, where this is what you mentioned is perfectly true. So whatever you mess up in the geostationary orbit will have consequences for long term. In the low Earth orbit, there are really early stage startups, there are university teams, there are programs that shoot satellites into this orbit, which are allowed to do that. They're orbiting for a few years, and then they naturally combust, if you want. They're naturally rupturing in lower because of the higher temperature, because they are falling down to Earth.
Hmm. And also another one derived from that about validation and certification. Like, how do you validate for this system? Like compared to automotive, you go to a rig and do vibration, and you do EMC and temperature shock. Like how does it relate to what we are used to with automotive?
Right. So this is a classical engineering development approach, basically as a V model development. So it's classic. On the left-hand side of the V model, deriving the system requirements, breaking it down to components, and then verifying these component and system requirements against all your iterations where you build hardware, where nothing works, you build it again, some parts work, and so on. And then you validate them against the requirements either from your customer. Our customers are companies building satellites or companies building launchers, and they need to show compliance against certain standards. So there are standards coming from the European Space Agency, the EASA, or, well, most famous NASA standards, because they are used mainly by the launcher provider. So if you are a launcher provider and you want to make sure that the payload you're going to shoot up in the skies is at least as robust, that it doesn't break up while I'm launching that payload, it doesn't mess up with my communication, it isn't endangering my team operating with that launcher, and so on. So they have a massive set of rules which are normally defined by the launch provider, for example, SpaceX, and that's where you have to show compliance again.
Okay.
Great, thank you, Johannes. I would like to go back to the design phase of the batteries, and we were discussing what are the differences between automotive batteries and space, not aerospace, but space batteries. Do we find some difference in the chemistry or even in the format with which you are using for space applications?
Interestingly, there's a strong tendency in the automotive industry to go into large format prismatic or large format pouch cells because of their extreme cost efficiency, also volumetric and gravimetrical energy density. And these tendencies we cannot really use in the space application because pouch formats, first of all, are not suitable to be exposed against vacuum conditions. So we need hard cased cell formats like the cylindrical cell or prismatic cell. And secondly, we rely still on quite small cells. Like we do not really tend to go to these massive BYD blade batteries or whatever, because our systems are just in the below 1 kWh range, and therefore we cannot really build batteries with these larger formats.
You
So
wouldn't have the voltage, no? You would have only like 1, 2, 3 cells and maybe 20 volt. So you cannot really power anything with that.
right, and we want to have a bit of a redundancy here as well. So rather we integrate multiple smaller cylindrical cells where if one cell fails in open condition, let's say because of the shock vibration, we have loss of the electrical connection of that very cell, we do not lose the whole system and therefore lose the complete mission. So there's a strong tendency in space to use small cylindrical cells like 18650, and we at Excellion, we transferred that and we are using now the 21700 cell format, which is the cell format which Tesla actually industrialized heavily for the Tesla Model S. And there we see, on the one hand side, great mechanical stabilities, uh, especially against vacuum, shock vibration, because it's quite a solid steel cylinder. And on the other hand side, it's widely adopted. So you get various different cell chemistries in this very format. So it's important to say that our startup Excellion does not develop its own cell chemistry, and we don't have a huge cell production line because that would be a multi-billion euro investment. But we are procuring and buying the best cell chemistry in this small cylindrical format. And therefore, we can guarantee that for either application, if you rather look into a high power application like an e-pump, providing high power for, let's say, 10 minutes to a e-pump of a launcher system, we can find you the right cell chemistry which is optimized for this short and powerful discharge cycles. Or we look into cell chemistries which are rather optimized to sustain long and numerous cycles. And therefore, this is again spreading out and getting a bit complex. So you cannot really say that there is one space battery because there is no space, not one space applications. There are various applications you can think of. Again, like this very small to this very, very big systems for launchers. And therefore, one has to think about different cell chemistries you can apply. And that's part of the magic in Excellion to provide battery systems, which on one hand side can scale, becoming bigger for big applications, but are also modular to accept different cell chemistries, which are all in that cylindrical format.
You're muted, Martí.
You're still muted, but that's great breakthrough.
Great, thank you. And yeah, and also regarding you said cycling might be in many applications a very important topic where maybe iron phosphate batteries will be more performant than typically NMC, nickel, manganese, cobalt. Um, what about the thermal gradients? You were explaining the day and night or day and eclipse situations. Which are the range of temperatures which we were seeing or the batteries seeing over there?
That's a really specific question to that very application you're looking into.
Okay.
So the satellite has a lot of means to control
Mm-hmm.
and to limit this temperature gradient. If you think of a satellite being exposed to that heat up and cool down condition every 90 minutes, that will cause a massive thermal stress to all
Mm.
components, not only to the
The
battery
cell.
system. And therefore, the satellite itself applies means like radiating heat and reflecting
Mm-hmm.
incoming solar radiation. And that's like the first barrier of defense. And then this battery itself is buried within the very satellite structure and thermally decoupled from that outer structure so
Okay.
that this heating up and cooling down cycles are not crazily stressing the temperature cycles of the battery.
Mm.
And furthermore, we have an active heating capacity on our battery systems, which is just a resistive heater in the end, where we actually try to find a sweet spot to, on one hand side, not always heating up the complete battery and therefore heating the complete satellite, but on the other hand side, enabling a safe operation, which
Mm-hmm.
is for most cell chemistries something like 20 degrees Celsius.
Mm-hmm.
And this is something we try to control in the end by a control loop, measuring the temperature in the satellite, measuring the temperature in the cells or in the battery pack,
Mm-hmm.
and then using the heater control to get that heater resistively warming up the battery or not.
Because usually outside in this Leo we have how many degrees? Like minus 100, something like this. Don't
Well,
know.
it's hard to discuss temperatures where there
Okay,
is nothing, right? So, what's the temperature in a vacuum? So
nothing.
it's
Okay.
theoretically minus 273, but in the end, it's always dependent on the vehicle,
Mm-hmm.
on the system where the battery is integrated, and it's dependent on how this system is exposed to radiation,
Mm-hmm.
and how the thermal management in that very vehicle is organized. To put it simply, the battery tries to be separated from the structure because
Mm-hmm.
the structure extremely varies, especially when we look into launcher again. So on the other side of things,
Mm-hmm.
in a launcher, you have liquid methane, liquid oxygen, which is at minus hundreds of degrees Celsius. And then on the other hand side of the launcher, you have the propulsion system, which is a combustion cycling burning these liquids in multiple thousand degrees Celsius. So these exposures are quite extreme. Therefore, we invest a lot in mechanically ensuring that there's a thermal isolation of the battery, and then having a closed control loop, which is which is then setting the ideal operational temperature for that battery.
Closed control loop, it means a refrigerating system.
No, closed control loops in terms of we measure the temperature
Okay.
decentrally and then have a mean of heating up the battery in accordance, doing this independent of any higher systems.
Okay.
So no closed loop
No
refrigeration.
closed loop like cooling and of course for satellites, I think you explained the like the um, yeah, PTC or something like a small heater, but you won't have a coolant or something like this which is going through the battery and cooling the battery or just temperating.
Not there's none requested now because the ambient temperature is normally lower than what the battery itself actually accepts or prefers as an environment. And when you think of a launcher system, you always have the possibility to mount the battery in different locations. And then we would prefer rather a cool environment where we can isolate and then heat than a too hot environment where we would need that expensive and complex refrigeration cycles.
No, just thinking like for a launcher, like if the like if you need to, if you have a lot of power in the turbo pumps, would it make sense to have the cryogenic fuel going around the battery to cool it down, or is it like over engineering stuff?
No. It's actually not over engineering. That's something one could discuss.
Okay.
That is a
Make a patent, Miquel.
No, I
already
guess
happened.
it's already happened a couple of times.
Okay.
No, but I was just wondering. I don't know whether it makes sense.
It's true. So payload electric components are cooled in launcher systems by the propellant, not at minus 200 whatever degrees Celsius, but let's say after they already expanded
Okay.
or heated up, and this is used as cold plate.
Okay. Cool.
Excellent point.
I'm
So
having lots.
we won't have any patents today,
No, I don't
but
think so.
I think
Not today, next
we
time.
understood a little bit about how batteries work.
Yeah, cool stuff. It's fun. It's fun. I always have lots of fun when talking about space stuff. Like it's not my field, but it's always fun to talk about it and learn. So,
Learn a little bit. Yeah,
what shall we move to the questionnaire, Martin?
yeah, we can move.
All right.
Sure.
So we always start with a hot take, bold opinion, something that it's against the mainstream, maybe, or something that may that it's not as comfortable to say in the in the industry, or I don't know, whatever feels good to you to talk about.
I think something uncomfortable for Europeans is to really wake up now and to see that Europe is not part and is certainly not on the table anymore of the nations being able to use strategically the space and to participate in the massive potential in using low Earth orbit for future business models on the one hand side, but also using the low Earth orbit for strategic means like telecommunication, like Earth observation, and so on. So everyone in Europe must be clear that there is no possibility for us in Europe to fly to our ISS, which we funded once, because well, we were dependent on the Soyuz system by the Russians, or now we are dependent on Elon Musk Falcon 9 with
What What
the
about
Crew
Ariane?
Dragon. So Ariane is not for
Okay.
manned flight. So, and Ariane is too expensive to compete with the Falcon 9. So there has been a dramatic price reduction of a factor 10 already between Ariane 5 and Falcon 9, and there will be another factor 10 price reduction between the Falcon 9 and Starship. And there is no real trajectory in Europe anymore how to compete and how to participate in that field. And if I look at Europe, I see so many technologies where we are not participating anymore. Think of AI, think of open AI and the development when it comes to artificial intelligence. Like, which European company are you thinking of when it comes to artificial intelligence? Like, I even don't know anyone. And then think of electrification. Like, Marty, we see that automotive industry in Europe was great when it comes to electrification. But now we see a dramatic price reduction in electric cars coming from Asia, coming from BYD and NIO and space. It's the same. Like, the Europeans need to wake up that we lose another total domain of technologies where European companies were leading in the past, but due to, I think, strategic errors, but also maybe because we're in some parts too slow, we really lost being on the table and being part of major strategic decisions which are relevant for Europe. Think of Starlink and the impact on the Ukraine war. So how can it be that a military strategic relevant system is in the control of one guy, Elon Musk, somewhere in California,
Texas.
who is
Well,
deciding?
No, California.
but
Okay, he's in Texas now most times, so he's not in
that's
California.
not even a state. We're talking about enterprises, private enterprises. So
About one guy, like one
in this case,
personal
it was like
opinion.
this. But I think there's also maybe other examples where Europeans we do bring good technologies with not only innovative but also good quality. Um, but anyhow, sorry, it was your
But
bold opinion, so I want.
It's not. It's it may be true that we bring in certain aspects, certain individual technologies. That's true, Marty. But do we still have the role of really deciding over complete domains of technologies and being leading in a complete ecosystem? And what I wanted to say is, in artificial intelligence, we lost control of that ecosystem. In means of mobility, we are losing it. And when it comes to new space applications, when it comes to all these fields of getting satellites into the orbit, getting launches flying cheaply and reusable, we are again losing this domain. And that's why we are fighting for an European autonomy on space, bringing back these capabilities, bringing this know how back to Europe. And we need a strong strategy in Europe, and we need that funding, to be super honest, to get this autonomy strategically back in our hands to launch systems in whichever orbit we want to launch it, and being able again to provide manned transportation means also back in European hands to be autonomous from any election in the US, which is also coming end of this year, and being independent of any autocracy like Russia or maybe in future China, which will make us
To
dependent
make
again.
Europe
I
great again.
I love the discussion. Like we could have a whole episode, I think, on this. I would like to make a comment. The innovation in space in the US didn't came from the mostly from the Northrop Grumman, from the Boeing, from the Lockheed Martin, and the large fundings from NASA. It came from startups. It came from SpaceX, but also now from Blue Origin, from Rocket Lab in New Zealand, and from many others. So what we need is more of these guys, well, like you, that fund that do your own startup, that start your own thing and go fight out there for your ideas, right?
Yeah, it's nice that you put it that way. But on the other hand side, it's maybe cool that small teams like us from a small university in Munich try that. But in the end, it is a question of funding and strategic orientation. So SpaceX received really, really early on massive programs
Yeah.
coming from NASA, because NASA understood that there's a strategic relevance to have a strong industry
Okay.
where they can really tap in, get the technology, get the capabilities in the US localized. And if you ask someone in ESA whether they are gonna supply or whether they're gonna um, allow any company launching
Well,
their
there are small
payload to
programs,
India,
no,
which has
but
not 10 years of
Well,
experience.
we have
So,
PLD starting from Spain. We have also
no, but there is
Sateliot,
Pangea. There is Pangea, which has
Pangea.
a funded program from ESA, but it's like compared to the money we're talking in the US, probably is in
Of course,
the
it's not, but
it's in different
these are
range.
billion contracts coming from the NASA being funneled into SpaceX. So you have a
Yeah, yeah,
different ecosystem. So I'm talking about a startup ecosystem being capable of funding
yeah,
deep
yeah.
tech innovations, as it happens so often in the US. It doesn't necessarily happen in Europe. And to be super honest, it's quite often that we hear, okay, guys, you do a great job in Europe, but you have to go to the US to
To do the
become
big boys thing.
large.
maybe we can link this with a second question, which is, would you have a career advice? Yeah. Do you have to, if somebody wants to make some career in aerospace, in
Space.
space, sorry, does he or she have to go to US better?
Nah, nah, nah. If you want to start a career in deep tech, I will always recommend that during the time in university that you have to join these crazy teams building real stuff. Like in most universities, there's a team on Formula E building crazy electric race cars. There's normally a team building a Hyperloop vehicle. You can think whatever you want about the outcome of these programs. The important thing is that already during university, you go through the pain of developing hardware, developing software in a team, get that all integrated in whatever system you could think of, get it tested against real life requirement, and you're gonna learn so much more lessons than in any lecture. I can tell you that this is a great starting point. So most of our students, they come from these teams. So in the Technical University of Munich, there is a team on the rocketry group which build actually launchers. Like, of course, small micro launchers bring small payloads in absolutely low orbits, but these lessons are like unparalleled. These people bring with you. Then there's a team building a small CubeSat satellite. So it's an actual satellite. Students are designing, manufacturing, testing. Everyone is gonna get signed on that very satellite, and they launch one, I think, every 3 years. And these are these experiences to harvest during your time in university. These experiences are unlocking any career ambition you have, because then you're perfectly prepared. Let it be automotive, let it be aviation, aerospace, you name it. But really engage with these early groups, fail fast, make stuff which is stupid in the beginning, then you will have a great time as a professional.
Thank you.
And the last one, I think it goes in the same direction as on the hot tape, like vision for the space industry in the EU, but maybe you can go more specifics into the startup ecosystem in Bavaria or in Munich. How I mean, I've seen a couple of startups coming up in the space industry in the Munich area. So how do you see that? Is it becoming like a hub for this technology?
Yeah, I think new space in particular is heavily embedded in other industries. So there is no actually need for a satellite if it's not embedded in a broader environment. So we talk about communication satellites in low Earth orbit providing super fast internet to your electric cars, Marty, because you have to have worldwide massive coverage of broadband internet connectivity, which not necessarily is provided by ground stations. So you have to have that that ecosystem transfer from automotive to new space, or from medicine to new space, or from Earth observations and sensing to these new space. And that's really greatly happening in the, let's say, southern Germany or broader European environment. And therefore, we see a lot of potential on the one hand side by the embedment in the industry, but also from the talent transfer. So we are hiring, recruiting people from the automotive industry because they bring most of the capabilities and tools we would require. And lastly, there is still, from a venture perspective, quite a lot of programs and support in Munich coming from the technical university. There's a organization called the Unternehmertum, which is ensuring that startups starting in the TUM are perfectly, let's how should I say, provided a environment and an incubation phase, which is fostering their ambition to become a bigger company. And this incubation phase is extremely important because it's so hard in Germany to start a company from scratch, and you need various means of support when it comes to office spaces, when it comes to laboratories, when it comes to workshops. All of that you cannot provide right from the start, and there the technical university provides the right environment, and that's
I
something we
think
talk
there's
about a lot.
also a cluster called Bavaria, I think, something like this.
In Bavaria,
Bavaria,
right? So these are,
with air in the middle.
yeah, right. These organizations, these clusters are combining all the interests of the aviation industry, but also space industry, and representing them against the rule makers and against other entities to make sure that in Bavaria we keep that industry localized and to ensure that there's a growth potential for this high
Okay, so
tech as well.
there is a certain ecosystem on space in the Munich area, let's say in Bavaria, and
Absolutely.
I hope you can take profit of this with Excellion, so everybody can use your batteries not only in this area but also maybe also in the US or in other countries, because I think also the space industry is very international, so there are always projects combining companies of different countries, not even different yeah mm, not only from within Europe but combining several continents, no. um,
Absolutely. Yeah. So our first satellite, which will fly with an Excellion battery, is actually launched by a
mhm.
Falcon 9 by SpaceX. So this is an international business, which is great. But on the one hand side, we also see that the world is drifting apart. Like as a European country, it's super important. As a European company, sorry, it's super important for us to stay within the realms of the NATO
Mm.
territories, because we have to ensure the strategic independence in Europe and in Northern America, but we cannot interact with any Chinese, Russian, Indian companies so far, because we have to keep that, let's say, strategically decoupled.
From an IP perspective, you mean, or this decoupling, or
Right. So there's a strong tendency to ensure it not only from the IP perspective, but also from the
okay,
procurement sourcing perspective. So if you think of a strategic autonomy of an European space industry, it cannot rely
strategically
on
on
any
any.
product or any material is coming just from China. Otherwise, we would end up in the same means of dependency as Germany has been dependent on Russian gas. Everyone has been dependent on medicine products from India,
Okay.
and so on and so on. So there, if you really think the autonomy perspective through, you have to think of decoupling and de-risking, and that's something really part of the DNA of many new space startups right on. And it's a strategic demand from the European Space Agency to ensure that their supported companies, and we get support directly from the European Space Agency, are localized or localizing their procurement just from European soil.
Great. So we started talking about technology. We end up talking about geopolitical stuff. Thank you very much, Hannes. It was a great hour, great interview. And wish you the best for Excellion and for what it has to come. Whether you come back to Earth, to cars, or just fly to Mars or even farther.
Thanks a lot. It will be a ride, and I'm looking forward to all of that. Thanks a lot for having me.
So,
Awesome.
have a nice evening.
Have a great one. Bye-bye.